Welcome to the video lecture of course code U18ESIT404 Digital System Design. And I am Dr.B.Dhanalakshmi, Professor, Department of Information Technology, School of Computing, Bharat Institute of Higher Education and Research. And today we are going to see about the topic asynchronous sequential circuits. And first we will see what are sequential circuits. Sequential circuits consist of a combinational circuit to which the storage elements are connected to form a feedback path. And the sequential circuits are specified by a time sequence of inputs, outputs, and internal states. There are two types of sequential circuits, namely synchronous sequential circuits and asynchronous sequential circuits. And now we will see about synchronous sequential circuit. The change of the internal state that occurs in response to the synchronized clock pulses and the data that are read during the clock pulse are referred as a synchronous sequential circuit, where we can identify it using the rising edge which are triggered. It is supposed to wait long enough after the external input changes for all flip-flop inputs to reach a steady value before the next clock pulse. And now we will see the unsuitable situations. Here, the inputs can change at any time and cannot be synchronized with the clock. The circuit here will be very large and a cost in time of transitions cannot be avoided. And now we will see about asynchronous circuits. And here they are not synchronized by a common clock. The state change that happens immediately after input changes. For a given value of input variables, the system is stable if the circuit reaches a steady state condition. The circuit reaches a steady state condition when y is equal to the overall signal, which is referred as capital Y for all I. The transition from one stable state to another state that occurs only in response to a change in the input variable. And now we will see the fundamental mode operations of the asynchronous circuits. The input signals change only when the circuit is in a stable condition. The input signals change one at a time. The time between two input changes must be longer than the time it takes the circuit to reach a stable state. The timing is the major problem here in asynchronous circuits because of the unequal delays through the various paths in the circuit. And now we will see why asynchronous sequential circuits. Asynchronous sequential circuits basics here involves no clock signals. So the internal states can change at any instant of time when there is a change in the input variables. And asynchronous sequential circuits have better performance but very hard to design due to the timing problems. And now we will see the strong reasons why we need asynchronous circuits. Accelerate the speed of the mission where we no need to wait for the next clock pulse. Simplify the circuit in the small independent gates. Necessary when having multi-circuits, each having its own clock. And now we will see the analysis procedure involved in the asynchronous sequential circuits. The analysis of asynchronous sequential circuit proceeds in much the same way as that of the clocked sequential circuits which are asynchronous. From a logic diagram here, the Boolean expressions are returned and then transferred into tabular form. The analysis of the circuit starts by considering the excitation variables Y1 and Y2, which are referred as outputs, and the secondary variables Y1 and Y2 are referred as inputs. The Boolean expressions here, where Y1 is equal to xy1 plus x dash y2 and y2 is equal to xy1 dash plus x dash y2. The next step is to plot the y1 and y2 functions in a map. And we combine the binary values in corresponding squares. The following transition table is obtained in the further slides. The transition table shows the value of y is equal to y1, y2 inside each square, and those entries where y is equal to y are circled to indicate the stable condition. The circuit has 4 stable states where the y1, y2x is equal to 0, 0, 0, 0, 1, 1, 1, 1, 0 and 1, 0, 1, and 4 unable states that are 0, 0, 1, 0, 1, 0, 1, 1, and 1, 0, 0. And now we will see the state table of the circuit, as we explained in the earlier slide, is shown below, where the present state 0, 0 here, and when the next state, when the input x is 0, then we get the next state transition values as 0, 0. And when input x is 1, then we get the next state as 0 and 1. And when 0, 1 is given as the input, and when x is 0, then we get the next state values as 1, 1. And when x is 1, we get the next state values as 0, 1. And next, we get 1, 0 as the present state inputs. And when x is 0, we get the next state values as 0, 0. And when x is 1, we get the next state values as 1, 0. And when the present state value inputs are 1, 1, and when input x is 0, the next state values are 1, 1, and when x is 1, the next state values are 1 and 0. And now we will see about the flow table. So in a flow table, the states are named by letter symbols. So here is an example where the flow table with 4 states with 1 input. And next table shows you the 2 states with 2 inputs and 1 output. So in order to obtain the circuit described by the flow table, it is necessary to assign to each state a distinct value. So here the flow diagram shows, the first flow diagram shows with 1 input and 4 states available, and the second flow diagram clearly explains with 1 output and 2 inputs. The 2 states with 2 inputs are given. And here this assignment converts the flow table into the transition table, which is shown below. So the transition table here clearly explains the output y, which depends on the Boolean expression x1, x2 dash plus x1 y. And the next transition table map for the output where z is equal to x1, x2, y. And here is the logic diagram where it is shown below, that is shown below this, the diagram where we have x1, x2 as the inputs and z as the output. And here we use the AND gates, OR gates and the inverter gates. And now we will see about the race conditions. A race condition exists in an asynchronous circuit when 2 or more binary state variables change the value in response to a change in an input variable. When unequal delays are encountered, a race condition may cause the state variable to change in an unpredictable manner. if the final stable state that the circuit reaches does not depend on the order in which the state variables change, then the race is called the non-critical race. So in the non-critical race, here the circuit does not depend on the order in which the state variables gets changed. So here is the example of non-critical races which are illustrated in the transition table. So here the possible transitions are given where the transitions are given in the circular form, that is circled here in the flow tables. The transition tables below illustrate the critical races. So here you can clearly see the critical races where the transition table switch over from the inputs to the output state. So we can see the transition that happens from 00 to 11 and 00 to 01 and 00 to 10. And the right hand side flow table, we can see the transition that happened from 00 to 11 and 00 to 01 and further 11 and 00 to 10. The races can be avoided by directing the circuit through a unique sequence of intermediate unstable states. When a circuit does that, it is said to have a cycle. So here is an example of such cycles which are given in the below diagrams. The state transition can be explained in the diagram A from 00 to 01 and from 01 to 11 and from 11 to 10. And the second diagram B table shows the state transition from 00 to 01 and further from 01 to 11. And the third table C, which denotes the unstable condition where the transition becomes cyclic from 01 to 11 and from 11 to 10 and from 10 to 01 back. And here are the stability considerations. So here an asynchronous sequential circuit may become unstable and oscillate between the unstable states because of the presence of the feedback. The instability condition can be detected from the transition table. So here the following circuit explains, the logic diagram explains the presence of the feedback where we can find the unstable state. And now we will see how the transition table can be derived for the unstable circuit. Those values of y that are equal are circled and represent the stable state. When the input x1, x2 is 1, 1, then the state variable alternates between 0 and 1 indefinitely. In all the other conditions, we get the stable state between the values either 0 or 1. And now we will see the circuits with SR latches. The SR latch is used as a time delay element in asynchronous sequential circuits. The NOR gate SR latch and its truth table are given here in the logic diagram where we can see the cross-coupled circuit. So here in the cross-coupled circuit, we can see two NOR gates and where R is given as an input, one of the input, and S is given as one of the input, and where the next state is determined by Q and the Q dash. And the truth table is given on the right hand side where when S and R values are 1 and 0 respectively, then the next state Q and Q dash values will be 1 and 0. And next condition, when S and R values are 0 and 0, then the next state Q and Q dash value remains the same. And when the S and R values become 0 and 1, then the Q and the Q dash values become 0 and 1. And when S and R value now changes to 0 and 0, then the Q and Q dash, the next state values will remain the same, 0 and 1. And when S and R values are 1 and 1, then the Q and Q dash values will become 0, 0. And now we will see the circuit showing the feedback. So this diagram C denotes the circuit showing the feedback where the output Y is given as the input which forms the feedback in the S latch. The Boolean function of the output is given by SR dash plus SR, which is equal to S into R dash plus R, which is nothing but S. So Y can be given as, the output Y can be given as SR dash plus R dash Y. Now the reduced excitation function for this particular Boolean function can be given as Y is equal to S plus R dash Y when SR is equal to 0 and Y is equal to S into R Y dash, which can be given as S dash plus RY. And now we will see the transition table for the above given circuit. The behavior of the SR latch can be investigated from the transition table, and the condition to be avoided here is that both S and R inputs must not be 1 simultaneously, and this condition is avoided when SR is equal to 0. That is, using AND operator of S and R must always result in 0. When SR is equal to 0, which holds at all times, then the excitation function derived previously can be written as Y is equal to SR dash plus R dash Y, and which can be expressed as Y is equal to S plus R dash Y. And here in the transition table is given clearly where we can see the transitions involved, and the Boolean expression also has been mentioned, which is Y is equal to SR dash plus R dash Y and Y is equal to S plus R dash Y when SR is equal to 0. And here it is given the NAND gate SR latch and the corresponding truth table. So the first diagram A here defines the cross-coupled circuit where we have the SR latch. So S is given as the input and another input for S NAND gate, the first NAND gate is the output Q dash is given as one of the input in the first NAND gate. And second NAND gate here involves two inputs. One is R and other is the output of the first NAND gate, which is Q. So here, when S and R are allotted with values inputs 1 and 0 respectively, then the next state Q and Q dash is given by 0 and 1 respectively. And when S and R are 1 and 1 respectively, then the next state Q and Q dash is given by 0 and 1. And when SR inputs in having 0 and 1 value, then the Q and Q dash will remain 1 and 0. And when S and R changes the inputs to 1, input 1 respectively, then Q and Q dash, the next state value remains the same with 1 and 0 respectively. And when S and R having 0 as the input, then Q and Q dash will have 1 as the output. So here diagram C denotes the circuit showing the feedback where the output Y is given as the input for the second NAND gate along with R input. And the output of the second NAND gate is given as one of the input to the first NAND gate. So thus forming a feedback. And D shows the transition table So where we have SR, two inputs involving Y as the another input. So the next state values are given here and the transitions are given in the circle. Now we will see the design procedure where there are a number of steps that must be carried out in order to minimize the circuit multi-complexity and to produce a stable circuit without any critical races. So the design steps are given in the following steps. The first step involves obtain a primitive flow table from the given specification. Reduce the flow table by merging the rows in the primitive flow table. Assign the binary states variables to each row of the reduced flow table to obtain the transition table. And the fourth step involves assign the output values to the dashes associated with the unstable states to obtain the output maps. And the last step involves simplify the Boolean function of the excitation and the output variables and draw the logic diagram. So here is a design example along with the specification given. So design a gated latch circuit with two inputs G, which is a gate, and D data, and one output Q. The gated latch is a memory element that accepts the value of D when G is equal to 1 and retains this same value after G goes to 0. Once G is 0, a change in D does not change the value of the output Q. So now we will see the step 1, primitive flow table. A primitive flow table is a flow table with only one stable total state in each row. The total state consists of the internal state which is combined with the input. To derive the primitive flow table, first a table with all possible total states in the system will be needed. So on the right hand side, the flow table is given where the states, the different states involved, the 6 states A, B, C, D, E and F are given with the inputs D, and the gate inputs are also given, and the corresponding output values of Q is also given. So in state A represents when data D is 0 and the gate input is 1, then the Q value is 0. And when D value, the next state B represents when data D is 1 and the gate input value is 1, then Q will also be 1. And now the gate input becomes 0. So now without any queries, the Q will also become 0. And now the data D from 0, it is getting transition to the value 1. In this case, the gate input will represent the Q output, which is 0. So after state C, now state D and E state represents the gate input 0 with data input 1 and the Q output will be 1. And last state after E, F state represents the data D is 0 and the gate input is 0, then the output Q is 1. Each row here in the above table, the previous slide specify the total state and the resulting primitive table for the gated latch is shown below. So what we are doing here, first we fill in one square in each row belonging to the stable state in that row. So first row, the stable state is identified as A. And next we recall that both inputs are not allowed to change at the same time. We enter dash marks in each row that differs in 2 or more variables from the input variables which are associated with the stable state. And last, we find the values for 2 more squares in each row. The comments listed in the previous table may help in deriving the necessary information where the dash here indicates the don't care condition. And now we will see the step 2, which represents the reduction of the primitive flow table. The primitive flow table can be reduced to a smaller number of rows if two or more stable states are placed in the same row of the flow table. The simplified merging rule are as follows. Two or more rows in the primitive flow table can be merged into one if there are non-conflicting states and outputs in each of the columns. Whenever one state symbol and don't care entries are encountered in the same column, the state is listed in the merged row. If the state is circled in one of the rows, it is also circled in the merged row. The output state is included with each stable state in the merged row. Now, we need to apply these rules to the primitive flow table which are shown earlier in the previous slide. To see how this is done, the primitive flow table is separated into two parts of having 3 rows in each part. So here is the primitive flow tables where the figure A shows the states that are candidates for merging, and B figure shows the reduced table where we can see the after merging the reduced table can be seen in the figure B. Now we will see the step 3 where the transition table and the logic diagram has to be drawn and the assignment of distinct binary value to each state converts the flow table into a transition table. In the general case, a binary state assignment must be made to ensure that the circuit will be free of any critical races. There can be no critical races in a 2-row flow table. Therefore, we can finish the design of the gated latch. Assigning 0 to state A and 1 to state B in the reduced flow table, we obtain the transition table. The transition table is, in effect, a map for the excitation variable y, and the simplified Boolean function for y is then obtained from the map as y is equal to dg plus g dash y. There are 2 don't care outputs in the final reduced flow table. Alternatively, we replace the don't care by 1 when y is equal to 1 and dg is equal to 0, 1. The map reduces to q is equal to y. If we assign the other possible values to the don't care outputs, we can make output q equal to y. So the first figure A shows y is equal to dg plus g dash y Boolean expression where when the data is 0 and the gated input is 0, then what will be the output y? So it has been clearly explained in the diagram A. And B diagram where q is equal to y. So where we can see after assigning the other possible values to the don't care outputs, what will be your output? So that is given in figure B. And the corresponding logic diagram is given at the last. So where we can see the data D and the gated input G is given to the AND gate, and then the G is applied to the inverter, that is NOT gate, and which is one of the input for the second AND gate along with the input Y, and in turn the outputs of the 2 AND gates are given to the OR gate, and the corresponding output Y is again given as a feedback to the second AND gate. And step 4, here we see assigning outputs to the unstable states. The stable states in a flow table have specific output values which are associated with them. The unstable states have unspecified output entries designated by a dash. The output values for the unstable state must be chosen so that no momentary false outputs occur when the circuit switches between the stable states. This means that if an output variable is not supposed to change as a result of the transition, then an unstable state, that is a transient state between two stable states, must have the same output value as the stable state. And here is the diagram where we can see the circuit with SR latch, and the assigning output values to the unstable states are given on the right hand side. So the mapping of for S and R inputs are given, and how the outputs values are assigned even to the unstable states are given in the figure A and B on the right hand side. If an output variable is 1, 0, then change the value as a result of a change in the state, then this variable is assigned as a don't care condition. And if a 0 is entered as output value for unstable state C, then the change in the output variable will not take place until the end of the transition. And if 1 is entered, the change will take place at the start of the transition, since it makes no difference at all. So this reduction of state and flow tables, when the change in output occurs, we place a don't care entry for the output associated with the unstable state. So this is how the design procedure is clearly explained in asynchronous circuit, and we will meet in the next lecture. Thank you.